Hi everyone, my name is Andrei Barbu. I'm a research scientist across the street in CSAN. I'm going to tell you about work with a whole bunch of folks from CBMM. What we work on is the interaction between vision and language, because today when you put this into CaptionBot, what you get out is there's a table, there's a room, and it's indoor, and it's not even very sure about that. I don't think any of us wants to trust our children with robots that take care of them when this is what they can tell about what's happening. Our idea is, and this is very closely aligned with the four-module structure, is that your ability to perceive the world very closely interacts with your ability to describe it in natural language and reason about what's going on. And this is what really allows you to come up with more reasonable descriptions and understanding of scenes like that. And we have a theory about how this might be happening that brings together problems from different fields. But I don't want to tell you about this today. What I'm going to tell you about is a problem that we hit while thinking about this, which is how can children possibly learning language? If you go to an NLP conference today, a natural language processing conference, the account of language learning that you will hear is that sentences are heard, and at some point the parser sees some parses, and if after a few thousand of these parses, the child is eventually able, or the parser is eventually able to parse new sentences. This is obviously not a model of child language acquisition that's anywhere near reasonable. Kids have to be doing something else. They have to see the environment. Maybe they have to also interact with some humans. And this perception of the environment has to be enough for them to acquire language. And we just sent out a paper for publication with a model that does exactly this, that learns the structure of language without ever seeing a single annotated parse for a sentence, simply by observing actions and interactions with the environment. And part of what's interesting about this is simply getting a robot to do it. There we go. Simply getting a robot to do it practically. Also, the thing is, whatever language is, it has to be learnable in this setting. And this is one way to try to get at some of the inductive biases and language universals that are built inside your brain. We know that if language is an arbitrary context-free grammar, it would never be learnable, even with direct supervision, never mind with the super weak supervision that you get out from vision. One of the things that make this very challenging is that the parse, there exists an object, is true of every possible sentence, so you need some additional inductive biases in order to make this work. The other thing I want to tell you about is a project that started a few years ago, part of CBMM, that quite a few postdocs have been involved in, which is this idea that computer vision is vastly overstating the performance of object detection. So if you read in the New York Times, there are routinely stories that say object detection is solved, and indeed if you go to a computer vision conference, I've had audience members interrupt me in the middle of a talk and tell me, why are you saying that object detection on your data set, it's mostly a solved problem? That was awkward, and he got a long answer that I don't think he enjoyed. What's going on is the standard of science and computer vision is considerably lower than it is in something like psychology. In psychology, you know that you need controls for your experiments, and you know that your data can't be correlated with the correct answer. Computer vision people don't know this yet. And so what we've been doing is gathering a data set of about 300 different object classes, about 100,000 images, which is on the order of scale of ImageNet. That has controls in it where the rotation of an object doesn't inform you about its class, where the correlation with the background doesn't inform you about the class of the object, where we have human subject data for every single image, and we know what people think about these objects and how they can recognize them. One of the interesting things that happens when you do this is amazing way that people manage to misinterpret your task. So in this case, people did great. We told them that the red arrow should be towards the cutting bit, the yellow arrow should be towards the handle. But you know, what happens when you don't have the object that we want you to get? Well, you search online on Google image search until you find the rook that's in the right position that we ask you, and then you take a picture of it. I'd say that's sort of malicious compliance. But how do you make sure that we don't mistake your object for something else? Well, of course, you label it so that we know it's a chair and it's not some other object. So then we keep having to add caveats to the task to get people to stop doing things like this. But the data set will be collected very soon. Just to end, I want to tell you about the next step with the data set, which is we really want to understand much more about human psychophysics. we all know that if I show you an image for 10 milliseconds, you can't really perceive much. And if I show you an image for 5 seconds, you basically perceive everything, unless you're Megmi and Gabriel, in which case you're still searching for Waldo. But nobody really knows exactly what's happening in between. No one's characterized this curve of accuracy over time very carefully. Is this really a sigmoid or not? We don't know. Is it some other polynomial? Even more than that, are there discontinuities? If you're a believer that there's a feed-forward network for the first few hundred milliseconds, and then at some point a more complex kind of system takes over, there's no reason to believe these two systems work at exactly the same rate and provide exactly the same amount of information. Maybe that means there are some discontinuities either in the actual values or in the gradients of this function. To get at this kind of data. We also have no idea what this function is really a function of, if you want to predict it. Does the shape or texture of the object impact this function significantly more than anything else? And maybe this is a better objective function for networks, given that networks these days, object detectors are mostly recurrent, like a ResNet. You can unfold it in time as much as you would feel like. Maybe it should make the mistakes that people make. Just to wrap up, I want to tell you for 30 seconds about a conversation that only happened because of CBMM, and it only happened at the site visit, and that was with Matt. We happened to be standing in front of the poster for the object data set and talking about the rat experiments that Ling mentioned, and we were thinking about the sort of things that Jim does with monkeys, where he shows them an object of one class, and then he asks them to pick the image that corresponds to the same object class. And people and monkeys seem to do very well at this, but we started to wonder, how about mice? What do mice think about object classes? Do they have conception? Because, there's a good reason why a mouse might prefer not the chair that looks really comfy, but the box, because it has the same materials. In real life, it's probably more important to know whether it can hide in something or not, or whether something is soft. Who knows? It's quite interesting. We have no idea about how other animals generalize between object classes. We may or may not do this, but this is definitely a conversation that never would have happened were it not for CBMM.